All right, physics, here we go again. Electromagnetic induction part 3. Two things I want to do in this lesson. One is talk about a unique case of when a conductor is moving in a magnetic field. And the other thing I want to do is sort of take away the mystery of these induced currents. It still feels to me like Faraday's law and Lenz's law are kind of mysterious how I get this current. Why should changing the magnetic flux give me a current? Why do the currents oppose the change? What's the deal there? So I want to demystify that a little bit. So remember, Faraday's law said that the rate of change in magnetic flux is what gives you your voltage. The quicker you change the flux, increase or decrease, the bigger the induced EMF, the induced voltage. And Lenz's law said the current that gets produced by an induced EMF will flow in a direction that opposes that change. So in this lesson, I want to show you that Faraday's law with Lenz's law, that little negative symbol, is really a direct result of something we already know about, the Philby force. And this one is, I think, easier to understand. I can appreciate that if a current, I, moving is a bunch of moving charges, and so it will have a magnetic field around it, and that magnetic field will interact with an external field. That makes sense. And so I would expect an electric current to interact with an external field, which would give rise to a force. The direction is sort of hard for me to understand, but I get it. I get the basic idea that a current will interact with a magnetic field, giving rise to a force, this Lorentz force. What I want to do in this lesson is show that that is really what causes there to be induced voltages. These two formulas are really two sides of the same coin. And I'm going to do a little proof to show you that. And to follow my proof, you're going to need to remember the following, that velocity is distance divided by time, that work is force times distance, and that whenever you do work, you transfer some energy. Work is always a transfer of energy, either kinetic or potential. Voltage, this will be harder for you to remember, whether it's induced or whatever, is energy per charge. So voltage is, if you like, joules per coulomb. And electric current is coulombs per second. How many coulombs pass by a certain point per second? Coulombs per second. If you can remember all those three, you can follow my proof really easily. All right, so imagine you have a conductor, piece of metal, inside a magnetic field coming out of the page. And of course, metals are full of electrons that are free to move around those valence electrons. If I were to grab that conductor and pull it sideways, I'm going to yank it in this direction, then that means all the electrons will be moving this way in a magnetic field. And you know what happens when a charged particle moves in a magnetic field? It experiences a force. Which way would that particle experience a force if I start pulling it to the right? Hopefully, you are manipulating your left hand, not your right hand because it's a negative charge, and hopefully you are putting your fingers towards you, out of the page, your thumb to the right, and you will see that, that electron should experience a force upwards as I move it to the right. So it would look something like this. I pull to the right and electrons would flow up to the top. And that would create a situation where you have a potential difference. A negative charge would accumulate here, leaving positive charges accumulated here. It's almost like you've got a battery. So long as you're moving it, you've got a positive and a negative end, a potential difference. So if I could connect that bar in a circuit, maybe I could drill some holes through my metal rod and then just run a wire through it, like rails or something, and I could yank this along those rails. Then I could extract I could take advantage of that electric potential. And now I could close my circuit out. So when I do that, and I pull, now the current can flow. It doesn't need to just accumulate. So with my negative here, my positive here, then positive current, conventional current would flow this way. And I'd be able to see that. I'm having to pull with my external force. And do I have to fight against any other force, or did I get that current for free? Well, we already learned in the last lesson, no. The induced current is going to flow in a direction that opposes that change. Let's just quickly check. Did that current obey Lenz's law? Now the positive current is that way, right? We know that electrons go up, but the conventional current we would label as going downwards. Now, so what happened as I pulled that across, I really increased the area of my loop. So I increased the magnetic flux out of the page. So the current would be like, yo, I don't like that. I will try to create a magnetic flux into the page to oppose that. So if I put my thumb down here on that green current down, my fingers will be into the page over here, thus opposing all of these increases that are happening as I move it across. So yeah, that obeys Lenz's law. But that doesn't tell me why I had to fight against something. That just tells me, yeah, it's going to create a magnetic field into the page. So what? Well, this current that's flowing down to oppose the change, it's flowing in a magnetic field. And we know what happens when a current flows in a magnetic field. It experiences a Philby force, right? What direction would that Philby force be? Well, put your thumb, use your right hand this time because we're talking about conventional current. Put your thumb down, put your fingers out of the page, so you should have your hand like that. And we can see this induced current is going to experience a force, a Philby force, to the left. So when I pulled to the right, a current flowed down, which experienced a force to the left. So the very current that I created is fighting against me. The more current I create, the bigger this Philby force. And so I don't just get to induce a current in this circuit for free. I have to fight against a force. So I'm going to have to do work. This external force is not zero, right? It's going to be equal to this. In order for me to pull this rod at a constant velocity, I'm going to have to fight against ILB. I'm going to have to match that force, where L here is the length of the conductor in the magnetic field, that distance there. Let's dig deep into the mathematics here. So same picture, I just sort of shrunk it a little bit. So in order to pull it at a constant velocity, I'm going to have to match that force. So the external force would have to be equal to ILB. The work that I would do to pull it across that distance and generate current as I do so would be equal to force times distance. The force I have to supply is ILB. So the work I'd have to put in is ILBD. Now let's remember that I can write current as charge per time, which gives me that. And what I'm going to do now is I'm going to whip that Q over here to give me work per charge is LBD on T. Work per charge, energy per charge, that's voltage. That is voltage, energy per charge. And distance divided by time, well, I can replace that. That's how quickly I was pulling it. That's velocity. And so I get induced voltage is equal to BLV. Well, I like to say BULV. This is a unique formula. It tells you the induced voltage when a conductor of length L cuts across magnetic field lines of strength B at a speed V. Bulv. That formula is on the formula sheet, and you have to solve problems for when conductors move through magnetic fields. That wasn't actually what I was aiming at, though. That was just a little detour. So I'm going to undo that. I'm going to get my V, and put it back as D on T. And check this out. L times D, that's really length times width. That's really an area. And not just any area. As I moved the rod from here to here, that was the increase in area. I started with just this. I finished with all of this area. So the green box there, L times D, that really represents my increase in area. It's my delta A. So now I have B times delta A on T, and hopefully you're recognizing that. Looks familiar, doesn't it? B times delta A. B times A, that's a change in flux. So from those simple force and energy analysis, I can see that my induced voltage really is proportional to the rate of change in flux, in this case an increase in area. So I get Faraday's law from Philby and from the work formula. That's all I want to do really today. I'll quickly give you one example where we apply this Bulv, this unique induced voltage in the case of a conductor. This is the general formula, well, with the N and the negative. This is a specific formula. So here's a plane. Planes are made out of conductors, made out of metal, and has a wingspan of 40 meters. It's flying horizontally over the North Pole at 100 meters per second. Now, the North Pole, which is a magnetic south pole, the field lines are going to be going into the ground, which from this perspective would be into the page, hence the little crosses there. I made a mistake the other day. I said the strength of Earth's magnetic field is about 50 milliteslas. Yeah, I was wrong. It's like 50 microteslas, or 5 times 10 to the negative 5. Oops. So yeah, it's weak. It's only strong enough to push around little tiny compass needles. 50 milliteslas on average. Anyway, so yeah, this plane is flying through a magnetic field, cutting across those field lines. What would be the induced voltage across the wingtips? Hopefully you can see this is really similar to the situation we just had. And so that's a conductor, 40 meters wide, moving at speed V, so I can use my Bulv formula. B times L times that. What's the size of the voltage? 0.2 of a volt. Not bad. Could you charge your phone? Could the pilot be like, sweet, I'm getting this voltage for free? Could he simply connect that circuit and put his phone there or something and charge it up, like get that current? Would that work? I'll let you think about that. The answer is a big fat no, and I'll let you try to figure out why. Why can't you get the current to go in a circle and charge up my phone? All right, you should have a read of 6.1. Hopefully that will make sense of what I just said. You should do the dot point exercises, do all 10 questions there, and optional, I'm going to give you a lesson at the end of the week to do Star Wars problems, no lecture. But if you're crushing it right now, you could do those too. All right, Kiddly Winks, hit like, subscribe, happy quarantine.